Yes.
Can you explain a little bit what an elementary row like operation is? Like,
Yes, it's adding a multiple of row to a different row, swapping two rows, or multiplying a row by non-zero.
Oh, I didn't know that's what they were. Okay.
Other questions? Okay, what we're going to talk about today is what is known as Cramer. I think you're going to see very quickly, I think what Cramer is, that computationally, this sucks, right? It's not very good at all once you get beyond maybe 2 by 2 or 3 by 2 matrices. So why even bother? Well, the reason we're bothering is because of the consequences of Cramer, because it actually will allow us to do a couple of neat things. Number one, it gives justification for the last theorem that I'm going to give you, which is basically how to transform areas and volumes. And number two, it's going to give us a general form for the inverse of a matrix, which I promised you earlier in the course, right? We know what the inverse of a 2 by 2 matrix is. If the determinant is not zero, how do you do it in general if the determinant is not zero? I'll be able to give you a formula. It will still practically probably be better for you to row reduce the matrix in most cases, but we've got something anyway. So, so here's some notation. I've got some n by n matrix. Let's say that A is equal to A1, A2, AN. Now, the notation I want to introduce is AI. What do I mean by this? This is what I obtain when I take matrix A and I replace the I column with this vector B. So this will look like A1, A2, AI minus 1, B, AI plus 1. So this notation just means take whatever happens to be in the ith column of A and replace it with this, whatever this vector B is that I happen to have. And with that, I can give you Cramer's rule. Now I'll show you how to do it. Let A be an invertible n by n matrix. So it's important that A be invertible. We'll see this towards the end. If B is in Rn, then AX equals B has a solution, well, let's say unique solution X given by the way, before I tell you what it's given by, let me point out that since this since A is invertible, that's how I know I've got a unique solution. If they were not invertible, perhaps I didn't, and that's what's important. And in fact, I know what the solution is. X vector is A inverse B, right? But I've got a more convenient way to write this and frame it for them. And I'm going to tell you what each of those components is. Xi is the determinant of AIB over the determinant of A. So really what Cramer's rule does is it gets you a nice, pretty little formula for every one of these entries, right? X1 is determinant A1B, determinant A. X2 is determinant A2B, etc. So really what you're doing is you take A and you replace for X1 the first column with B and figure out the determinant. Replace, find X2, replace the second column with B and find the determinant, and so forth, so on. Notice determinant of A always appears on the bottom of this formula. So that's another kind of, we need this matrix to be invertible, otherwise I'm dividing by 0, and that would be a problem. Anybody want to criticize Cramer's rule? Time for a little complaint session. Right? Anybody want to criticize this from a practical point of view if you actually want to get on your horse and yeah, we all hate that, right? It does. Doesn't it sound like a lot of work? I mean, because what have I got here? Okay. I've got n things to figure out. I've got n plus one determinants, right? I got to figure out the determinant of A, which is always in the denominator, then these n other determinants, right? That sounds like death on a hot plate, right? Nobody wants to do that. But guess what? I'm going to do it anyway. But I'm going to do it with a, this is one where Cramer's rule, if you're fast enough with 2x2 determinants, might actually be quicker. Let me give you the system here. And 5x plus 4y is equal to 2. So let's look at the roles that everyone's playing here. My matrix A is 7, 6, 5, 4. And my vector B is 8, 2. Everybody clear where all that comes from? Now, Cramer's rule says that I've got to figure out the determinant of A. Do that. What is it? Agreed. -2. 28 minus 3. Okay, and there's only two things, X and Y. And so by Cramer's rule, X should be determinant of A. Determinant of something else. And Y should be determinant of A over the determinant of something else. And let's see what I got going for me here. Well, for X, which is the first variable, I should be replacing the first column with that, right? So it should be like 8, 2, and then the next column is 6, 4. Everybody down with that? And for the other one, I should be replacing the second column of A. So I've got 7, 5, and then 8, 2. By having that. So let's see what we get here. This is going to be what? 20. So I get -10. And this one, the determinant of this is what? 14 minus 40, so it's -26. If you're quick enough with this, that was reasonably fast. You know, especially since these are kind of obnoxious numbers, right? And it might be just as fast. 3 by 3, I almost promise you it slows down from row reduction. Now, the first question that I want to tackle before I start using Cramer's rule. So I'm not really going to use Cramer's rule a whole lot of solving systems because it's very tedious and ominous, right? Yes.
If you just find the unique solution,
Yeah, that's exactly right. That's right. And actually, again, you gotta love linear algebra, you gotta love math in general, test it. right? Minus 10 is what, 13? That's minus 70 plus, well, let's make sure I did it right. Minus 70 plus 78, say, let's do it. Minus 50 plus, 52 is, looks like I. Okay, so why does Cramer's rule work? Because I only use it for a couple of other things, to kind of get some stuff to help us out. Well, what is this? Well, so let A be A1, A2. So I'm gonna use my old notation, my interest thing. And if I use this, by the way. Suppose IN is the N by N identity matrix. If I follow in lockstep with my notation there, how would I write the columns for IN? Right, I use my little e's, right? Column one at the top, one in the six places. And so. Since AX equals B, we have. I want me to make clear. As X. Let me make clear that we're all talking. This is my new notation, so this is A as it was. And this is the square matrix. It's almost the identity matrix. What have I done? I've taken the identity matrix and I've replaced the ith column with whatever X is. So this looks, all the columns look like the identity matrix, except for the ith one that looks like X1, X2 all the way down. What is this? This is A times E1, E2, X, En. And this is in the ith column. Now, multiply that sucker out. Right. And we've seen enough matrix multiplication, I guess, now. Now, this thing is actually equal to AE1, AE2, AX, AEN. Because that's how we multiply matrices. You can just go in like that, like A times these columns. So, okay, yeah. This is equal to. What happens when I multiply A times E1? What do I get? I get the first column of A, don't I? So this is A1. This is A2. So I get the second column of A. What do I get here? I get B right there. Well, I'll make this multiplication, really and what is this? This is AIB, right? Because isn't this just the matrix A with the ith column replaced by T? Okay, so. It's all coming together. So what do I have now? Well, I have. I'm gonna kind of summarize what I've got here. This is where I started. Is equal. Now, take the determinant of both sides. Oops. That. Right, because the determinant of this is the determinant of the two pieces second. That's one of the lessons we did last. Everybody okay? Now, the only thing left that I think I really need to do is I really need to kind of figure out what this determinant is. And let me kind of draw a picture of this point. I know what the determinant of A is. It's the determinant of A. I know what this is. Determinant of A. This is a little bit mysterious to me, but let me try to look at what this is. So if I look at I, X, what this is 1, 0, 1, 0. Okay. How do I get the determinant of this, right? I mean, it's almost the identity matrix, except it's got that stupid rodent column in the middle, right? Any ideas?
Well, no, never mind, it would be upper triangular, X goes on the parent screen.
Yeah.
Won't it be the height entry of the X, X column?
The force is strong with this one. Yes, it is. It would be, how did you see that?
Because if you do the cross multiplication to get the identity matrix is just all one, but then you'd multiply by whatever that value is in the X column.
Right. The problem with this, there's something to overcome, and what there is to overcome is this is neither, you can't expect this to be either a lower or an upper triangular matrix. Right, so you've got those exponents, but I mean, your intuition is absolutely correct about this. What I would do is I would expand. And so we're going to see your idea come to fruition about ith column. And something very magic is going to happen, right? Because it's going to be, there's going to be a sign in there, plus or minus, right? But basically the pieces of this are x1 times first cofactor, x2 next cofactor, and so on. Do I agree with that? So it's x1 times the first cofactor. And that's what you get when you ignore that row and column. Well, what can you say about the matrix that's left over? You know, actually, it's better. It's got a column of zeros, so it's determinant zero. So the x1 times whatever doesn't count. Right? What about the x2? This column and this. Now this one, when you nuke this out, actually this is a column of zeros for that one. Basically, everything that's off that diagonal has a matrix that when you collapse it has a column of zeros. So they're all zero. The only exception is what you're pointing to. And that is xi, right? Right here. And what is xi? Well, let's be careful about this. All that's left is xi minus one. What is the entry of xi? I mean, I know it's in the ith column, but it's also in the ith row, right? Right? Times determinant. And what happens in the xi that's actually right on the diagonal? When you remove its row in its column, what are you left with? Yeah, I did it. Besides one less. Notice it all comes together because this is minus one to an even power, so that's gone. This is one, and what we're left with is xi. So, what do we got? Determinant of A times xi, the determinant of AI. And now, since we're assuming that the matrix is invertible, this determinant is not zero, so you can divide by it. And I get xi is determinant of AIB over determinant of A. And there's the famous Cramer. Okay. Any questions on that? Questions? All right. So. Let me move on here. I want to do another thing. Here's an application. General inverse. Okay, so suppose A so suppose I have a invertible matrix n by n, and suppose I want to find A inverse. Let me make some observations. So the jth column and the inverse, let's call it X. So what I'm going to do is I'm going to try to figure out what all the columns in my inverse are, right? And what do I know about the jth column? Well, the jth column what should this be? Right, this should, that's exactly right. This should be there. But what I'm going to try to do is I'm going to try to build an inverse column by column. So I'm going to start off by saying jth column, but I'm going to call the jth column by the inverse. It must give all zeros except in the jth entry, right? Because I'm building the identity matrix, right? A times A inverse is infinite. Everybody comfortable with that? Okay, so how does that help us? Note the ith entry of X. So I'm going to try to figure out what this X looks like, making new J. The ith entry, so the one in the ith row is precisely the ij entry So if I go down the J column, 1, 2, all I, the ith entry of that is going to be the ij entry of the inverse. Okay. And so here's where Cramer comes. Because notice, this is kind of the setup for Cramer's rule. What do we have here? We have a matrix equation, AX equals B, in this case our B is EJ. And so IJ entry in A inverse is given by XI, so the I element of that column is determinant of AI EJ divided by the determinant of A. That's just what Cramer's rule said, right? This little formula here tells me exactly what belongs there. So let me kind of decode this a little bit. I'd like to kind of figure this out. So now consider I kind of wanted to show you what's going on here a little bit. And AI, remember what this is. This is the original matrix A we're inverting. I'll replace the ith row by EJ. So to kind of figure out what's going on here, I am going to cofactor expansion of AI EJ about I column or down the I column. And here's what I'm going to get. I get determinant of AI EJ is equal to, well, let's see, it's -1 I plus J. By the way, so let me point out here that this I column is all zeros and 1, 1. Everybody agree with that? All zeros and 1, 1. And the 1 appears in the J place, right? So that's position I plus J in the matrix. So it should be -1 to the I plus J, right? Times determinant A, and what do I have to, I actually need to move the J row in the I column. Everybody okay with me? Because all the other entries are zeros, so this is it. And notice, by the way, when I nuke the ith row and the J column, I did exactly what I would have had in the first place. Because when I removed the right, the J row and the I column, I'm removing the I column, and what's left over was only stuff that was originally in A. So this is the same thing as AJI. And of course, this is, by definition, the cofactor JI. Because remember, the cofactor JI is just -1 times the position times the entry of that position, which in this case is 1 times the determinant of AJI. And so this gives me what I want, because now the ijth entry should actually be what I get from, this right here, it should be CJI. On the permanent back. Because this mess here just turned out to be the JI drill back. So, in particular. You know, A is a variable. Then A inverse is given by. Be careful with this, C11, C21. C2, 2, C2, 3, 3, C3, all the way down to C, here, C, here, one over the determinant. Notice, let me give you kind of some notation here, for this might be a little. Notice it looks like the order's all messed up, right? But that's because this computation, you're actually reverse the roles by J. So let me give you the definition. In the cofactor matrix, if you ever heard that terminology, it's just C11 and 2, C1, 1, C22, N, 1, C2. That's what we're used to. This thing's a little different. What's the relationship actually between this?
Just the transpose.
That's exactly what it is. We'll call this C. CT, which is the transpose of this, C11, C21, C, M1, C12, C22, C22, C1, C2, C is called. That's what this thing is. And this is called, terminology for this is the classical adjoint. And sometimes the adjective. And there are many applications. So here's one application, Cramer tool. We now have a formula for the inverse determinant. It's still hard to compute actually, but it's got a nice compact formula for it. It's 1 over determined A times transpose of the cofactor matrix. This has applications all over the place. I'm teaching a rather pure math class, graduate class in topics and factorization of number theory. I used classical adjoint today on some completely different kind of number theoretic application. So this comes up all over the place. Let me use this actually to get something we already know. Let A be A, B, C. Let's compute the classical adjoint. Here, write this down, C11, C, one, C12, C2. Okay, what is C11? It's the determinant of what's left over when you kill row and column one, right? It's the determinant of D, which is. Let's do C22. That's the determinant of what you get when you kill row two and column two, so it's just A. Okay, let me be careful with this. C21. I gotta kill the second row, first column. So what's this gonna be? It's gonna be D. Actually, Russ. There should be a negative there, right? Because remember, it's the determinant of what's left over times -1 to the power of the sum of the indices. So it's -1 to the 3 power, right? I'm gonna have the same deal here. There should be a minus, it should be -1 to the 3 power. And what do I get down here? It's what happens when I nuke the first row, second column. So it should be C. Yes.
You explain again what you're saying about it needing to be negative?
Well, because what Cij is it's -1, the I plus J. Comes determinant of Aij. The determinant of what's left over, we do this, but you also get that sign, so don't forget that, that's a common mistake. By the way, what happens when you multiply A, B, C, D, D minus B minus C, A. Well, AD minus BC, that's 0, this is 0, and this is AD minus BC, yeah. What does AD minus BC mean for this matrix?
It's the determinant.
And that is actually a more general formula. When you multiply a matrix by its classical adjoint, you get determinant of A times whatever the appropriate adjoint is, size of the matrices. And notice this gives you, this formula will actually give you the inverse of A if you can actually invert the determinant. Okay. Any questions? One final connection that's to talk about, and that is the following. One of the I feel questions for geometric. So this rectangle has some area, right? What if I do this? Can I make this? Bigger. The white parallelogram and the original rectangle. They're the same. Do I agree with that? I mean, it's kind of cavalier principle, but you can actually do some basic, geometry to figure out these things. Everybody comfortable with that? And that means something important. Because if you think of this as a vector, and that is a vector, this vector right here is a linear combination of things, right? So notice I have the same bottom, and I've added something to this vector right here to get the same thing. So here's the point. Here's the if A equals A, B, C, then the area of parallelogram determined by columns C is, anybody want to guess? There's an easy way to figure it out. Oh, you're so close. It's not quite, there's one thing you gotta be careful about. Can area ever be negative? No, it can never be negative. So let's take the absolute value. By the way, let me ask you this. Here's another reason this makes sense. What happens if the determinant is zero? What does it mean about that matrix? What does it mean about those two columns? If the determinant is zero, that means there's one or less pivot columns, right? So that means that one of the columns is a multiple of the other, correct? Because they're linearly dependent. So that means, what happens if I try to build a parallelogram and these two columns are multiples of each other? I'm not really building anything, right? Because here's what I'm going to do. I'm going to build myself a parallelogram. And then I do it like that. What's the area of that going to be? Zero. And so that makes good, wholesome, all-American sense, right? So the area or the determinant, the absolute value of the determinant actually determines this. And give you a more general figure. This is true also for volumes. Actually, you can go over it any dimensions like. I'll stop at 3, but if A, B, C, U, V, W, X, Y, Z, A, then volume of parallel pipe bed, just think box, determined by columns is the absolute value of the thing. Also, which is, I mean, this is like super groovy cool. And if any of you have seen calculus workers in the future, you will at least get an inkling of this somewhere along the way. Let me give you a stronger feeling. Theorem. Suppose E goes from Rn to Rn, and S is a reason. So think of space in 3 dimensions, think a planar area in 2 dimensions, but it can be something more general in higher dimensions. If M is matrix representing T and A of X denotes volume or area as appropriate, of the region X, then the area of yeah. This is a very powerful theorem because it allows you to do all this stuff. In the following sense, let me give you a quick example here. How many of you happen to know what the volume, and actually this region doesn't have to be bound by a straight line. So example. Inside ellipse. X over A. Plus y squared. E squared. Anybody have to know the formula for what this is? A zero. Here, B. So you have this ellipse here. Anybody happen to know what the formula for the area of that ellipse is? Well, let's find it. Consider T from R2 to R2 given by T of X equals MX. And it's the matrix A 0 0. I'll try to, because I've only got a couple minutes left, see if you can verify that this actually turns the circle into an ellipse. By the way, anybody know what circle goes to that ellipse in this transformation? If you consider x squared plus y squared equals 1, this is the vector 1 0, right? 1 0 right there. Where does this, when I multiply m by 1 0, where does it go? What does this matrix do to 1 0? Goes to A 0 right here. Right? About 0 1. Where does that go into this transformation? Well, if you multiply this by 0 1, you'll get 0 B, right? So basically what this transformation is doing is it's stretching A units along the x-axis and B units on the y-axis, right? What's the area of the circle by? Oh, I bet you guys can do that. Radius is 1, so it should be what? Should be 5. So, let's look at this formula here. The area of the circle transforms to an ellipse. By the way, take the equation of the circle and see if you can transform it to an ellipse. I just gave you 2 points, but it works everywhere. Equals the absolute value of the determinant of m times the area of circle. What's the determinant of that matrix? A, B, and the area of the circle. So the area of this circle is A, B, I. And again, the math takes care of you. What happens in the special case that A and B are the same? What does that look like? Looks like a circle. Does it give you the right quarter of A and B are the same? Yes, it does. Okay, any questions on this? This last one's very important. So look at some examples of this. Let me have any questions. Let me remind you that Friday, you will have a plot with you Friday. I'll try to post it this evening. You will have a substitute Friday. So obviously I won't be involved, but email me if you have any questions and I'll just see you by Monday. Matt, do you have any questions?
I don't even know anymore. I think I wrote that down. Like, they got two low people and say, but I think I should find it back.
Oh.
Sure. Yeah, I understand, but I think that's interesting.
Yeah,